would take the blame, worn out the way we let it stay. Taught how to celebrate it all out. I'd replicate your pain, climb down, if only for a taste. Hesitated, shallow, but full in all your veins, shadowed by every other wind. Hollow, and doubt can make it borrowed, a love that never came, followed in every other shade. Fade your love away. I never stray. In all your pain, in all your pain, I will carry you.
Hello, Mary.
Hi, Rima. How are you?
I'm fine. How about you?
I'm doing fine. I'm doing fine.
Wow, you look great.
Thank you.
Your hair is now longer than we met 2 years ago. Of course.
Yes. Yeah. I need to cut it a bit.
Okay, but it looks good with you. And Bu Yuda is already joining with us. Hello, Bu Yuda. Bu Yuda is still somewhere.
Okay.
Okay, we will wait a little minutes. Mary,
No
is that
problem.
okay? Yeah.
That's no
Okay.
problem.
I could make it all feel far away. I would raise my age out of this place, separate, but you're close for a better run. I was told, save your life as though you never known and ever owned. I should paint it out to feel storm. I'll trace space to hit the ground and run, shouting proud. When you're close for a better one, I was told, save your life as though you never know and ever own. Ain't it funny how we went nowhere? Ain't it funny how we went nowhere? Ain't it funny how we went
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. I hope you are doing well. Welcome to the second student course on Paleoceanography and Paleo-ENSO held by Oceanography Study Program. My name is Bella and I will be your Master of Ceremony in this beautiful Friday, 1st of September 2021. In this beautiful moment, I would like to welcome Professor Dr. Mary Elliot from Université de Nantes as our lecturer today. Bonjour, Professor Dr. Mary, the Honorable Dr. Irwan Meilano, ST, M.Sc, as Dean of Faculty of Earth Science and Technology, Institut Teknologi Bandung, the Honorable Professor Dr. Sri Yudawati Cahyarini from Research Center of Geotechnology, National Research and Innovation Agency as our moderator today. And of course, all of our beloved participants in this special afternoon. We have several agendas, so allow me to read several sequences of our agenda. Okay, the first one is opening and student course role, opening speech by the Dean of Faculty of Earth Science and Technology, early photo session with Pak Irwan, in case Pak Irwan has another important agenda to be attended, introduction of the speaker's profile by Professor Sri Yudawati Cahyarini, presentation session by the lecturer Professor Dr. Mary Elliot, Q&A session guided by Professor Sri Yudawati Cahyarini, and closing. There are also several rules that we need to follow for today's student course. For participants, please change your display name to agency or university underscore name. The participant must turn off the microphone, but it's optional to turn on or turn off your camera during the presentation session. When turning on the camera, the participants are expected to use the virtual background that has been provided, especially during the photo session. And since we will have early photo session, please open your camera now and use the virtual background. During the Q&A session, the participant can use raise hand feature for asking the question. The moderator will allow the participants to turn on the microphone and ask question. The attendance list will be sent via chat box after the presentation session by the lecturer. Untuk para peserta, diharapkan untuk mengganti display name menjadi instansi atau universitas underscore nama. Saat sesi materi, peserta diharapkan mematikan mikrofon. Untuk kamera dapat dinyalakan maupun dimatikan, itu opsional. Saat menyalakan kamera, peserta diharapkan menggunakan virtual background yang telah disediakan oleh panitia terutama saat sesi foto bersama. Dikarenakan kita akan mengadakan sesi foto bersama di awal, diharapkan pada peserta dapat menyalakan kamera sekarang dan menggunakan virtual background-nya. Saat sesi pertanyaan, peserta dapat menggunakan fitur raise hand untuk bertanya. Setelah moderator mengizinkan, peserta dapat langsung bertanya dengan menyalakan mikrofon. List kehadiran akan diberikan setelah sesi materi pada kolom chat. Without any further ado, let's step forward to the following agenda. That is opening speech from Mr. Dr. Irwan Meilano, ST, M.Sc, the Dean of Faculty of Earth Science and Technology, Institut Teknologi Bandung. The time is yours.
Terima kasih Nabila. Thank you Nabila. Selamat sore. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih Ibu Profesor Dr. Yudawati dari BRIN yang telah meluangkan waktunya yang berharga untuk berdiskusi dengan kami sebagai moderator pada sore ini. Good morning, bonjour, Professor Elliot. Thank you.
Thank you for inviting me.
We are very delighted to have you today. Thank you for spending your morning with us. We are honored to be your research collaborators at our Faculty of Earth Sciences and Technology. We are very lucky to have Dr. Rima as your collaborators, as the only Paleoclimate expert in our groups. And today, public lectures will focus on the Paleoceanography of the Indonesian seas, which is very difficult to pronounce. I'm earthquake scientist, so it's a new field for me, and it's very excited to be here. And Indonesia is a region that play a critical role in the global atmospheric and ocean circulations. The modern oceanography of Indonesia is very complex, as you might aware, due to the combined impact of the East Asian monsoon, the Australian monsoon, and the migrations of intertropical convergence zone, and also the El Nino in certain oscillations, which is reflected in the sea surface and the salinity changes in the regions. Dan kuliah ini merupakan salah satu dari rangkaian kegiatan dalam program Nusantara, skema riset Kemitraan Dasar 2021, di mana Ibu Dr. Rima sebagai ketua timnya. Terima kasih Ibu Rima di tengah kesibukan perkuliahan dan juga masih sempat untuk kemudian membantu penelitian bersama peneliti luar negeri, meningkatkan leverage dari fakultas kami, dan juga bekerja sama dengan University of Nantes dan juga ASTR di Prancis, dan berkolaborasi juga dengan peneliti dalam negeri, terutama dengan Pusat Riset Geotechnology, BRIN, dan Pusat Riset Kelautan KKP. This public lecture is one of the series of activities in the Nusantara programs, the 2021 Basic Partnership Research Scheme, collaborations in collaboration with foreign researchers at the University of Nantes, ASTR France, and collaborations with domestic researchers as well at the Geotechnology Research Center, the National Research and Innovation Agency, BRIN, and the Marine Research Center, Ministry of Marine Affairs and Fisheries. Professor Elliot's research focused on understanding the relationship between change in the ocean circulations in the past with the present climate change, which is a very important topics for Indonesia. And Professor Elliot's used geochemical traces such as stable isotope and trace elements measured on marine microfossils that allow us to quantitatively estimate the past changes in ocean salinity, ocean temperature with seasonal resolutions. So without further ado, allow me to open today's public lectures. Again, thank you, Professor Elliot, to be with us today. Terima kasih dan selamat mengikuti kuliah umum ini. Semoga Anda semua mendapatkan manfaat dari kegiatan sore ini. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, thank you, Pak Irwan, for the opening speech. As I mentioned before we move to the next agenda, let's take a photo session with Pak Irwan as a dean.
Okay, I need to make sure that I have the appropriate background.
For the participant, please use the virtual background because we will have a photo session.
Okay, and who will be the leaders for these photo sessions?
I will take the lead, sir.
Okay.
Okay, let's wait until 1 minute more before I take the photo. Okay, let's take the photo now. We will take 3 sessions of photo. So we will begin now. Okay, 1, 2, 3. Okay, another one. 1, 2, 3. Okay, and last one. 1, 2, 3.
Okay, good. Thank you so much.
Okay, thank you, Pak Irwan and Professor Mary and
Yeah,
Yuda and
welcome.
all participants for the photo session. The next agenda will be led by Professor Dr. Sri Yudawati Cahyarini. Bu Yuda is a researcher at Paleoclimate and Paleo-Environment Research Group at Research Center for Geotechnology, National Research and Innovation Agency. Bu Yuda will introduce Professor Dr. Mary Elliot and guide us until the Q&A session. To Bu Yuda, the time is yours.
Terima kasih, Mbak Nabila. First of all, I would like to welcome to Mary and the Honorable Dean of Faculty of Earth Science, Institut Teknologi Bandung, Pak Dr. Irwan Meilano.
Terima kasih, Bu Yuda.
Distinguished participant, ladies and gentlemen, and thank you for attending this general lecture. Assalamualaikum warahmatullahi wabarakatuh. I don't think that I would like to introduce Mary because maybe before it's already introduced by Dr. Meilano, so maybe I will not take long time. So I think I would like to welcome to Professor Mary to deliver the lecture, and this lecture will be in 60 minutes and followed by the question and discussion in 30 minutes. So Mary, I think the floor is yours.
Okay, thank you very much. So I'm going to start sharing my screen. Desktop turn. Right. Can you see my screen now?
Yes.
No. Okay. Can you see it perfect? Can you hear me okay?
Yeah. That's
okay, great. Well, first of all, I'd like to thank all the organizers for inviting me. I feel very honored and really happy to be speaking to you all in Indonesia. I have been working with Sri Yudawati Cahyarini in the field in Indonesia for the last few years. And we do a lot of paleoclimate studies together. And I very much enjoy visiting your country when we are able to travel again. I look forward to that. Okay, so my talk is going to be about paleoceanography, and it's quite a general talk on trying to show you and discuss the links between climate change and ocean circulation patterns. So I've kind of changed the title just slightly in the sense that I've called it Paleoceanography, Ocean Circulation and Climate. Okay. Right. So the objectives of this seminar are highlighted here. And in a way, one of the messages I'd like to put forward is how us students and researchers in the earth science field can contribute to the debate about global climate change, and what kind of information can we bring, how do we work, and how do we work with colleagues who are working on climate change topics, more actual modern conditions. So a lot of my talk is going to be about comparing what we know from the past with modern conditions. And so basically, I'd like to present paleoclimate, paleoenvironmental studies. I'm not sure you're all doing paleoceanography. So the idea is to bring in even students and colleagues who are not very aware of this field into this seminar so that you can follow things. How do we record climate change, and what are the tools, the proxies, and the type of geochemical tracers that we use? Okay. Just to give you an idea of what direction I'm going to go in for this seminar, I'm going to be talking about how ocean circulation impacts our climate, and the two kind of major elements is that ocean circulation is a factor that redistributes heat from low to high latitudes. And the other important element is that it stocks a lot of the anthropogenic carbon dioxide that we are emitting into the atmosphere. The next step is that we're going to ask ourselves the question, what have we learned from paleoclimate, paleoceanography studies? It's good to ask yourself, for example, where the IPCC would be if we didn't have this vision into the past. What would we know of our modern day climate if paleoclimate studies had not been there to bring some additional information from the past? And we're going to ask ourselves a few questions about what are the modern threats to our ocean and how can that impact life in Indonesia, but all around the world. Okay. So just a few elements of modern climate for those of you who are not doing climate studies. The big energy or the big motor of our climate is incoming solar radiation, which is not distributed similarly from the tropics to high latitudes. So you have a higher concentration of energy and heat arriving in the tropical zone than you do at higher latitudes. And that is just the major element which is going to explain why we have warmer temperatures in the tropics and colder temperatures at high latitude. So this is a map of SST and atmospheric temperature. And what you can see straight away when you look at this little film is that the first thing is that tropics are warm, high latitudes are cold. And then you're seeing these seasonal oscillations. And then you start noticing that there's some patchiness in the distribution of temperatures, in that the continents tend to cool a lot more than the ocean. And they also tend to warm more than the ocean, as you can see here over the Sahara. So there's an element which is a first element, which is due to the distribution of continents, which acts upon the distribution of heat across the planet. And then the other element is the patterns in the ocean. You notice that even though the incoming solar radiation is going to be the same across the same latitudinal band, what you're noticing is that you don't have the same temperature. So if you're kind of looking at one side of this ocean basin and you compare with the other, you're seeing that there's a gradient in temperature. And this gradient is due to ocean circulation. And this is what we're going to be talking about today. Okay, so if you look at the surface of the ocean, you see that there's movement. There are oceans, there are currents in the ocean surface, and these currents are well known, they're mapped, we all know them today, and they are these ocean gyres. So for example, in the North Pacific, you have circulation which is going clockwise in this ocean basin. You see the same thing in the North Atlantic basin. And if you go to the Southern Hemisphere, you have a circulation pattern which is anti-clockwise. And this is due to the force of Coriolis acting on these fluids which are in motion. But what we're going to talk about mainly today is the capacity of these circulation patterns to redistribute heat across the latitudinal band. And we're going to see that there's a redistribution of heat. For example, we're going to look a lot at what happens in the North Atlantic, and there are reasons for that. And then we'll come back to the Pacific region afterwards. So in the North Atlantic, in this area, you have an accumulation of heat around the Bahamas, and you see that the Gulf Stream, which propagates northwards, is actually going to transport that heat. And this transport of heat can be actually estimated. And this is a plot which is showing the northward transport of heat in the northern hemisphere from the tropical region at 0 degrees latitude up until 90 degrees. And what we're seeing on this plot is that we have a northward transfer of heat from the tropics with a maximum around 40 degrees north. And then it kind of reduces back down to 0 up until the Arctic region. But what I'm wanting to highlight here is the roles of the ocean and the atmosphere in transporting heat. The ocean transports about 50% of the heat and the atmosphere about 50%. Okay, so what this means is that if you're going to modify ocean circulation patterns, you're going to modify the heat transport, this blue curve, which is here. And this is what we are doing when we're studying paleoceanography in the past. Okay, let's take another look at the Gulf Stream. So this is a map of sea surface temperatures, and you can see that you have these warm temperatures in the tropical Atlantic Ocean, and you can follow these this track of warm altitudes of the North Atlantic Ocean, and they mix with these Arctic waters. Okay, so there's not only heat which is being transported at this stage, there's salinity. And this warm waters and high saline, high salinity leads to high density of surface waters. And this high density is essential for explaining the global circulation patterns around the world. And here you have a map of what we call the global thermohaline circulation, and you see that we have warm waters distributed across the planet, and there are formation of these waters in the North Atlantic region, which then propagate south across the Indian Ocean and come back to the surface here at high latitudes. Okay, pattern is very sensitive to changes in density. It is a density-driven circulation, and if you change the salinity of, for example, of waters in the North Atlantic region, you are going to change the formation of these deep waters. So this pattern of ocean circulation is also going to explain, or the next slide I'm going to show you is going to show you a link between this ocean circulation pattern and the global carbon cycle. And what we're going to see is that these regions of deep water formation are also key in enabling the stock of carbon dioxide in the deep ocean. Okay, so carbon dioxide. We measure carbon dioxide in sites which are very distant from where there's human activity. And one of the key areas where we measure carbon dioxide is in the middle of the Pacific Ocean in an island called Mauna Loa. And we have been measuring carbon dioxide in this site since the late 50s. And we have this plot, which is showing the steady increase of carbon dioxide throughout the last decades. We have a mean plot here in black, and we have these oscillations of annual oscillations of carbon dioxide, which vary from summer to winter. So this site is located at 3,000 meters altitude. And the idea of the reason why we measure carbon dioxide in this site is to be able to have a well mixed and representative value of the global planet. Okay, so this rise in carbon dioxide is continuing. And what we're seeing is that we have an atmospheric growth of 4.3 gigatons per year, whereas we're emitting about double that per year through anthropogenic activities. And the reason why we're only seeing half the amount of carbon in the atmosphere is because we have a land sink and an oceanic sink. And the ocean absorbs about 33% of this anthropogenic carbon every year. So in a way, it's reducing the impact. It's helping to reduce the impact of the rise in carbon due to anthropogenic activities. Okay, where does carbon enter the ocean? It's in the areas which are highlighted in blue. And why is it that carbon is absorbed at these higher latitudes? It's because carbon is more easily dissolved into colder water than it is into warmer water. So that the cold oceans are more able to absorb carbon dioxide than the warmer oceans, which tend to be areas where we have a positive flux of carbon dioxide. So this map is basically showing the fluxes of carbon going in and out of the ocean. The areas in blue are the inward going fluxes, and the areas in red are the outward going fluxes, okay? So to come back to ocean circulation, this ocean circulation pattern and the formation of deep waters in the North Atlantic region is the key element to absorbing this additional carbon dioxide that is in the atmosphere. So this is a transect from the Southern Atlantic Ocean to the Northern Atlantic Ocean. And we are using a tracer in the ocean, which is the carbon isotope ratio. And you see that there is a gradient from higher values in the North Atlantic to lower values in and around Antarctica. And in the areas where we form deep waters, we have high absorption of carbon dioxide, and this carbon dioxide is then entrained and stocked in the deep ocean, where it can be stocked for long periods of time. So the key element is that if you change and modify this circulation pattern, you're going to reduce the capacity of the deep ocean to absorb anthropogenic carbon dioxide. Okay, so that's what we know from kind of modern day climates. If I do a point on what I've been saying so far, modify ocean circulation, modify the stock of carbon in the deep ocean, and we modify the redistribution of heat. Okay, so now we're going to look into the past and see what we can learn from paleoclimates and ask ourselves how the ocean, what role the ocean played in modifying these climates. Okay. Okay, so for those of you who've done a bit of paleoclimatology, you know that the planet has not always been in its current warm climate state, but there have been a succession of glacial periods and interglacial periods. During glacial periods, you have a large stock of ice all over the northern hemisphere. So here we have the Canada and the United States. Half of the United States were underneath ice, and then all the Scandinavian regions, the Great Britain, Scotland, which is where I originate from, northern areas of Germany were all underneath a thick blanket of ice, up to several kilometers thick. And then in modern times, the only element that is left from this northern hemisphere ice sheet is Greenland. Okay, now what we're going to look at is, well, what was the ocean circulation pattern like during this period of time, and what role did it play in producing this colder climate? So how do we go about studying past climates? We have lots of different archives that we can study. One primary source of information comes from the ocean. And for this, we use oceanographic vessels. This is the French vessel called the Marion Dufresne. And we are about 120 people on board. We do expeditions which can last a month and a half. And we go out to sea and we do sediment coring. So this is a small core, but it shows all the elements that are part of it. There's a cable dangling from the boat, there's a weight, and there's a long tube. And that tube can be more or less long. This is how it operates in the sea. So you lower the whole system down to the seafloor. And as soon as this counterweight touches the seafloor, it's going to release the coring device, which will then penetrate the sediment just by gravity. So we're not actually drilling or mixing sediments, we're obtaining a gravity core. And the idea then is that what we can keep a record of the sediment layers that are superimposed one on top of the other. So, and this is the type of archive that we use to reconstruct climate. Here's another photo of work on the deck. This is the weight, which can be up to 7 tons. There's the top of the tube. It's just come out of the water. And then we're working on the deck of this boat, cutting up these cores into sections which are 1.5 meters long. The longest core that we can do just by gravity is around 70 meters on this boat. So that's kind of how we work. What do we collect? We collect some ocean sediments, and these sediments are made up of a biogenic and a heterogeneous fraction. So basically it looks like brown mud, and when you touch it, it's very clayey, it's very sticky sometimes, and it has different colors, which usually relate to different periods of warm or cold climates. Okay, and in these sediments, the biogenic fraction can be composed of calcareous microfossils or silicate microfossils. And then we have these rock fragments, which have different sizes and can sometimes help us find the origin of the rocks that were broken up and transported into the deep ocean. The sediment, types of sediment that we get across the world. So this is just a map of modern day sediments. So where you have brown, you have basically deep sea clay. Where you have the white colors, you have carbon, calcium carbonate, so that you'll have microfossils such as foraminifera, coccoliths. And then in these other colors, I don't know how well you can see the different colors, but there's kind of a darker creamy color, and this is the silica-rich microfossils. And that's the diatoms, which you find a lot around Antarctica, and the radiolarian, which you find a lot around the Pacific, the central Pacific Ocean. Okay, so it is these microfossils that we are interested in, and they are microscopic in size. As you can see here, that's like 0.3 millimeters or half a millimeter. And then you do, from time to time, have these odd ones, which are very large in size, can be 10 centimeters in diameter. And these are all unicellular protists. They are heterotrophs, and they sometimes have a symbiotic lifestyle, and they are basically the plankton of the ocean. And in sediments, you find them in high concentrations, and you have those that are characteristic of tropical areas and other specimens which are characteristic of colder polar areas. And so it is these microfossils which we analyze and study in past climates. Okay. The coccoliths are other types of microfossils, and these are what make these big clay cliffs that you find in the northern regions of France. And these are also microfossils that you can find in sediment cores. Okay, so the sediment cores are, this is what a whole sediment core looks like, and I'm showing you this picture just so that you can see the changes in color, which are usually associated with different climate periods. And what you can do with these sediment records is reconstruct ocean temperature, you can reconstruct ocean salinity, and so you can reconstruct the density. And this is a very important element if you're studying changes in ocean circulation patterns. Another tracer of importance, and I'm going to be talking about in a few minutes, is that you can reconstruct ice volume and thus sea level changes through time, and some information on ocean productivity. So we literally have these core it is a highly active work, and we work very much together and collaborate on work on similar sediment cores to try and have multiple views on one site. Okay, so to do these paleoceanography studies, you got to be a little bit of paleo. You've got to know a little bit about sedimentology, and you've got to know a little bit about chemistry. Why? Because a lot of the tracers that we use today in paleoclimate studies call upon geochemical tool. And a lot of these measurements are basically stable isotope measurements, and mainly the ones that I use a lot are carbon and oxygen isotopes. So you're basically looking at ratios of elements of similar atomic number, but they have different masses. So they have different weights. So we tend to call the heavy oxygen 16 and the lighter oxygen, the heavy oxygen 18 and the lighter oxygen 16. Sorry, this should be up here. It's kind of got displaced. And then we do the same with the carbon. We do ratios of carbon, the heavier carbon 13 and the lighter carbon 12. I'm not going to talk about carbon. I'm just going to quickly talk about oxygen isotopes. And just to explain that this is one of the primary tools that we use in paleoclimate studies. And we measure the oxygen isotope ratio on these different species of foraminifera, and that oxygen isotope ratio of heavy to lighter oxygen is a function of the water temperature and the water isotopic composition. So it's often expressed in this delta notation, and I'm just presenting this because you're going to see that delta notation in some of my plots hereafter. And the delta notation is just a more practical way of providing numbers, and it's basically the difference between the isotopic ratio in the sample and the isotopic ratio in the standard. And all the labs around the world use the same standard, and thus our values are comparable. Okay. So we have paleo temperature equations, and I could spend an hour just talking about these equations, but I'm not going to. Just remember that temperature is expressed as a function of the differences between the isotopic composition of the calcite and the isotopic composition of the water. And this relationship has a negative slope, so that when you have basically warmer conditions, lower delta O values, you have more negative values, -3. And when you have colder conditions, so you go from 30 down to 5, you see that you have more positive, higher delta OH values. Okay?
Bahasa Inggris orang ngerti lah.
Okay.
Ini yang ngisi materi orang Inggris.
Okay. Okay, so they just can no longer secrete their calcium carbonate. Coccoliths, these are studies which have been done. We know that if we increase the amount of acidity in the ocean, we start seeing malformations of these coccoliths, and these malformations are clearly observed when you're doing these high-resolution images of these microorganisms. So basically, increased carbon dioxide in the atmosphere leads to more ocean acidification, which leads to threat on ocean ecosystems. And if you kill the corals, then you basically act upon all the ecosystems that depend on this environment to thrive and live. Okay, so that's a second consequence. Third one is sea level, and this affects directly regions where you have low-lying land. A lot of them in Indonesia, and some places are already being affected by this rise in sea level. So this is the plot that we have for sea level from the 1700s to 20 and projected values to the 2100. And here we are today, somewhere here, and you see that, well, there's a lot of noise in this record, but it's basically showing a rise in sea level in the order of 0.2, 20 centimeters, 30 centimeters. So you think, okay, this is not a lot when you think about it, but it's actually acting upon the erosion of coastal zones and the flooding of coastal zones more and more. And if you superimpose on that the storm tracks, which are increasing, then you have these ocean surges, and then this is a real threat to coastal populations. So the sea level rise is due to several factors, one of which is that if you increase the oceanic temperatures, which we know they're increasing, so you expand the ocean, and so sea level is rising. And then the other one is the melting of continental ice sheets, which is occurring more and more rapidly today. Here's a picture of Greenland, and in Greenland today, researchers have identified literally rivers at the surface of this ice sheet, which is transporting this fresh water, and sometimes it falls into crevices, and so then it is being transported into the ocean. The rapidity with which Greenland is going to melt is so difficult to predict that very often it's not included in any of the IPCC projections. So when an element is too uncertain yet, it's difficult to quantify, and so it's difficult to add to projections. And this is kind of an unknown factor, which I think is one of the dangerous ones, because if we melt too much ice, then we know again from the past that if we change the salinity of the ocean around these ice sheets, then we change ocean circulation patterns, and then we change the capacity of the ocean to redistribute heat, to stop carbon dioxide. And so there are these feedbacks, these positive feedback mechanisms that we are still urgently trying to understand. This is maybe one of the main points that I'd like you to take away from my lecture, is that we need to understand the different feedbacks within our climate system to be able to project and predict more precisely where we're going. And definitely studies from the past, lessons from the past have enabled us to show the links between past climate change and changes in global ocean circulation patterns. And there's urgency to understand better the different mechanisms of this climate change in order to better predict our future climate. I'd like to thank you all for your attention and listening to my talk today.
Thank you, Mary. That's really interesting topic. Now I think the first round for the question, maybe we will have 3 questions first, or anybody can just address the question directly to Professor Elliot. Any question? Okay. Who's next? Hanun Rahmi. Silakan, Mbak Hanun.
I have a question for Professor Mary. I'm sorry in advance if my questions is pretty basic, since I'm not really familiar with paleoceanography. But my question is, how can we reconstruct ice volume by only the ocean sediments?
Okay, so there are different ways of reconstructing ice volume. One of the main ways of reconstructing ice volume is by looking at fossilized corals that we find at different water depths. I didn't really have time to go into detail to explain how we do this, but the primary source is the coral record. So basically, when sea level was lower, then you had corals which lived at lower water depths. And so we're able to date these corals, calculate the depth at which we have found them today, and that gives us information on where the water level was at that time. The record that I showed was derived from the isotopic composition of benthic foraminifera. Now, benthic foraminifera are the ones that live in the deep ocean, where temperatures don't change a lot. So and because the isotopic composition is a function of both the temperature and the isotopic composition of water, if we are in an environment where the temperature doesn't change a lot or changes only a little bit, then the main record that we're looking at is the isotopic composition of the water. And in the deep ocean, the isotopic composition of the water is mainly going to reflect sea level change. Okay, so there are different sources of information, and they're all giving us the same number, 120 meters below sea level 20,000 years ago. But I thank you for your question. That was a really good one. I hope I answered. And okay.
Thank you so much, Professor Mary. I understand.
Okay. Thank you. Thank you for your question.
Next question from Ibu Aida Ambo dari Unhasen. Silakan.
Okay. Terima kasih. Thank you. Sorry, I cannot turn on my camera since my highlight camera is very bad. Yeah. Okay. Have your explanation about the Paleoceanography. I have heard and I have a little bit study on paleontology, especially because I'm a lecturer in marine science and relevant to field of corality of the coral, and sometimes I mention about the paleontology and the evolution in the coral reefs, and yeah, some of the species are the biota like foraminifers, Radiolarian sort of has been studied by our students. According to your information about the carbon sink, there are some theory about the carbon sinks, not only in the sediment, but also in the coral biota themselves. Yeah,
also,
yeah, the carbon sink. The carbon can be wrapped into the base of the coral, such as hard coral and soft coral, and it has something to do the carbon sink which hold the energy, and some of the biota such as the soft coral, that's some indigenous, not indigenous people, some people around the small islands put that soft coral to take the energy or the carbon sink from the soft coral. But yeah, but we haven't known the percentage of the capacity of this carbon sink, since we haven't any study about this yet. Probably I would like to hear that you may have any information about the carbon sink in the biota.
That's really interesting question. I think, are you referring to, there's a theory called the coral reef hypothesis? Is this? kind of what you're referring to.
Which one?
The role of the soft coral in the carbon cycle, I don't know enough about. I'm guessing that we know that the marine life plays an important role in absorbing atmospheric carbon. And so it's called what we call the biological pump. But to my knowledge, that biological pump was mainly active in the open ocean. Now, most probably coral reefs are also playing a role in the carbon cycle. And I know for a fact that the production of calcium carbonate by coral reefs acts on the carbon cycle. And it is even put forward sometimes as an amplifier in the carbon cycles when you go from glacial to interglacials, because obviously all the corals which are being produced today during a warm interglacial will die as soon as the sea level goes down and enters the glacial period. And then you have another phase of increased coral reef production when we are increasing sea level. I think it's very difficult when we're working in the past to have information on soft corals because they just don't, they're not preserved so that it's more difficult. So only studies on modern day corals could bring us some information there. And I'm not aware of any studies at this point, but it's a really interesting question. Yeah.
Gimana Bu, Ibu Aida? Is enough or still many other questions?
Probably because the coral can be tracing because it's the hard coral, so it can be traced for million years rather than the soft coral. But of course, you mentioned about the carbon can be the coral leave the material as a hematophytic typing. They leave the material to be component to be bound with the carbon instead of the soft coral. But the soft coral only maintain the carbon only in the very short time, since it cannot be like a hard coral that can be kept for many million years. So that's why I mentioned about the people around that make the certain of coral to be, such like people in the mainland, which always take some stones to make a batu akik, like a ring, akik ring, and they just make a mention that it has the carbon and energy already, and they make some kind of out of the what you call, for people just believe in something that's not real, and they just believe in the stone that have energy, but actually the energy comes from the carbon sink in the stones on the land. But that's the same principle with the people that take out the soft corals, because the hard coral is already cannot be taken their skeleton, except
Ibu bisa dipersingkat ininya, questionnya kalau masih ada lagi.
Just mention about the soft coral has the carbon sink that have a short term of carbon.
Yeah. Okay, thank you for the information. But as Professor Mary said, that it is difficult to get soft coral from the past I think most of the preserved coral is from the hard coral, as I know, even not all of the species, something like that. I think I will come to the next question. This is from ITB, Dimas Upadian. Silakan,
Yes,
Mas Dimas. Okay.
Okay, pardon me and thank you for the time. Greetings, my name is Dimas and I am from Oceanography. Greetings for Professor Mary, and actually I have two questions, but looking of the time, then I will only ask one question. This is about a paper from Stephanie et al., which was released in June 2021 about Paleo-ENSO influence on African environments and early modern humans. Conclude there is a tight correlation between moisture availability in East and West Africa that caused by Paleo-ENSO, where east side is humid, such as Tanzania, Congo, and west side is arid, such as Mauritania and Sahara area. Does this also happen in east and west side of South America? And yeah, but then again, we know that the east part of South America, which is humid, previously measured with west part of Africa, which is arid. Yeah, that's my question.
Okay, that's a really interesting question. So basically, Paleo-ENSO, are you meaning today or during the early Holocene? I think it's during the early Holocene that you're meaning.
Yeah.
Yeah. So during the early Holocene, there was a change in the, so if you look at Africa, I'm going to try and go back to one of my plots. There was one where, maybe not. No, I don't have one today. Okay, right. So basically, during the early Holocene, so that's about 6,000 to 10,000 years ago. So if you look at Africa, this whole area was humid. In modern day conditions, it's dry across this area. And this is due to changes in the intensity of the intertropical convergence zone. And the major forcing factor for this is the precession cycle, which is the 20,000 year cyclicity that I was discussing earlier. Now, there is a gradient across Africa today from east to west, the west being drier than the east. And this could be related to the presence of these upwelling systems that are here offshore. However, this area is tropical. If you go to South America, there's definitely a relationship between the activity of the upwelling and the dry and humid periods here on the west coast of South America. And we know that that in turn is related to El Nino activity. And so it's much more simple to explain these east-west gradients in South America through changes in ocean circulation patterns, which are related to variability of our climate. This is on a totally different time scale because it's like interannual, and so it's El Nino, La Nina situations. I am not sure about that being affecting Africa in the same way. I would have to look into that a bit further. I don't know if I fully answered your question, but that's what I can say about these east-west gradients in South America and the east-west gradient in Africa, which is not as strong as it is in South America. But I think that's also related to the land masses where you have these high altitude ranges that go from north to south in South America, and they also affect the transport of humidity and atmospheric circulation. Did I answer your question okay?
Gimana Mas Dimas?
Yeah, maybe I should read more about the answer from Professor Mary. And well, it's good if I can get more answer from Professor Mary in the future about that question.
Don't hesitate to contact me by email and we can discuss it more precisely. I'd be happy to help. No problem.
Yes, I'm glad, and thank you very much for the answer. That's all.
Yeah, okay. I will write Professor Mary email in the chat room maybe.
Yep.
Okay, the next question is from Nafisa Adyam. Mbak Nafisa, silahkan.
Okay, thank you so much, Ibu. Thank you so much, Professor Mary, for your lecture. That was quite insightful, especially for me. So from your presentation, we saw that our global temperature began to dramatically rising in the past years. And this issue also affects the ENSO, which also affects the monsoon system, right? So my question is, what will be the most significant effect? And would you like to share your opinion regarding the things that we should anticipate the most due to this process? Thank you.
Can you just repeat quickly the first half of your question? So you're basically asking how this is going to affect ENSO?
Our rising global temperature affects the ENSO and also affect the monsoon system, right?
Yes.
Yeah.
Yes.
And my question is, what will be the most significant effect that, and how can we anticipate, and what do you think the most significant thing that we have to anticipate the most?
Okay. Okay, that's again a really interesting question. So the ENSO and the monsoon are also evolving. And so today, what we're noticing is that each El Nino event, which is the warm phase of ENSO, tends to be associated with a pattern of warmer temperatures across the Pacific, which are more extended towards the north and the south. So basically, each El Nino event is warmer than the previous one, but also on a larger latitudinal band. So basically, my way of discussing this is not that global warming is affecting ENSO, is that there's an interrelationship between the two of them. So as the climate is getting warmer, El Nino is getting more intense, and then that is contributing to global warming. So I've put the plot with all the temperature records, and basically you see that this is not a straight line. The global warming has got little oscillations around it. And these oscillations are robust features. And if I were to position every El Nino year on this plot, you would see that every time there's a peak in the global temperature, it's an El Nino year. So El Nino is also contributing to this global warming pattern. So in a way, we can't even dissociate the two of them. Now, the projections for what's going to happen to El Nino in the future are still very uncertain. And actually, up until quite recently, there were quite conflicting results showing different tendencies. And this is something that we are actively working on within our community to try and better predict how ENSO is going to evolve. The monsoon is also evolving, and most studies are showing that this rise in temperature is related to more variability of our climate. But again, this is a feature that we need to constrain better, to quantify better, and it's definitely at the forefront of a lot of our research right now. So definitely an area that needs input from young future scientists. Lots of questions still need to be addressed and answered, and that is a very important one indeed. Thank you for your question.
Thank you so much for your answer.
Terima kasih. Is there any question? You can address question in Bahasa Indonesia and we will have to translate as best as we can.
Hello.
Okay. Another question from Pak Adin Adri, silahkan.
Hello.
Yes. Hello. Bonjour, madam.
Bonjour. Sebentar. Ini Bapak siapa ini? Yang ITB Adin Adri duluan ya. Nanti mungkin Pak Ali Kuden nanti ya.
Ya, oke. No problem.
Ya, silakan.
Yes, bonjour, madam. Je m'appelle Adin Adli. My name is Adin. I would like to ask you a question, but I'm apologize for my lack of understanding, but is it the climate change today is a normal cycle or not? And can we with the nowadays modern civilization, are we can survive this climate change? Maybe that is my question.
Okay,
Thank you.
so thank you very much for your question. I'd like to thank everybody for speaking English so well. It's really amazing. Thank you. And just so answering your question, today is not a normal cycle. I think that one of the plots that for me is important is this one. This one is showing that the temperature, the carbon dioxide, has values which have been unprecedented for nearly 800,000 years. It's on this plot here too. So we're up here and you can see that we just have not had this level of carbon dioxide. That level of carbon dioxide has existed in the past, but before human beings were around. During times when the position of the continents were completely different, and the biosphere and ocean circulations were completely different. So we are treading in a very unknown territory, we do need to change our lifestyles and our way of interacting with our environment if we want to be able to reduce the impacts. So, and I think it is down to reducing the impacts of what we are changing. Is our climate able to absorb this increase in carbon dioxide and go back to normal in its own? Yes, probably it would, but it would take time scales which go well beyond what we are used to be thinking about. So our timescales are years, couple of years, maybe a couple of decades at most. And I think the processes that are going to be required to absorb this carbon dioxide and go back to normal are more like thousands of years. So I think the only way is for us to adapt to what's happening and reduce emissions and interact with our environment in a more intelligent way, in that, you know, building in coastal zones is going to be a problem if we're going to have rises in sea level. And we need to think about how we can produce food for such a large population without it being so energy consuming. And there are lots of avenues to be explored. And I think this is why it's such an exciting topic, because everybody can bring an element to finding a solution. It is not one single solution, it is multiple solutions. And I think that the quicker we start looking and being effective at finding these solutions, the better it will be for all of us. I hope I answered your question.
Yes, thank you, Madam, for the answer. Maybe I will find another reference so we can survive with this climate change. Merci beaucoup.
Thank you.
Oke, terima kasih. I think there is still one question from Pak Halikudin.
Yeah. Okay. Yeah. Well, thank you very much for this opportunity. Yeah. I'm Halikudin Umasangaji from the University of Hairun in Ternate, North Molucas. And sorry for not being on the camera because yeah, sometimes we have the disturbance, perturbation of the connection here. So yeah, my question is, no problem. Yeah. So my question is, so we all know that Indonesian true flow plays the important role in terms of El Nino Southern Oscillation. So can you explain to us more about how the two items, the connection of Indonesian true flow to the El Nino Southern Oscillation, and how El Nino Southern Oscillation played an important role to the Indonesian true flow trends nowadays?
Okay, thank you very much for that question, because it's really, these are some of the kind of scientific questions that I'm working on, and one of the reasons why I'm so keen to be working in and around Indonesia. And yes, so I'm coming back to this pattern of what we call the thermohaline circulation, and you can see that Indonesia is a key area to be studied, because this is where the warm surface waters kind of transit back from the Pacific into the Indian Ocean. It's through Indonesia, and it's actually, if this wasn't such a simplified cartoon, this red arrow would actually go down here between Borneo and it's through the Makassar Strait.
Yeah, Sulawesi, Makassar Strait.
Exactly, yeah.
Between Sulawesi and Borneo Island.
Yeah, and so what happens, I wish I had a plot, I have some, but I need to go and look in my computer. So these surface waters come through the Makassar Strait, or, and there's another flux of water that comes down through here, through the South China Sea. And there is an antagonism between these two fluxes of water. So when there's an El Nino year, this flux tends to be stronger than this one here. And we don't know what the driver is. What we know is that they're related. And as a consequence, their El Nino, at least on very rapid timescales, is related to the changes in flux of this water flow going back into the Indian Ocean. And this is definitely something that we're interested in studying. Myself and Sri Yudawati Cahyarini, we've been working together. We work on corals and bivalves from around this area. And one of the questions that I have is definitely to understand how that flux of water has evolved through time. We know that there are variations. For example, during the Holocene, there was a change in the flux of water through this Indonesian through flow. We have not yet made the step to make very precise relationship between El Nino activity and the change in the Indonesian through flow. And again, this is a question very much that needs to be addressed and is, currently being addressed. So thank you very much for that question.
Yeah, you're welcome. It is clear enough. And yeah.
I'm sorry,
suaranya masih mute itu Pak Halikudin.
Okay. Yeah, it was clear enough for your explanation about how the Indonesian true flow patterns influenced by the El Nino Southern Oscillation. Yeah. thank you very much. And just for your information that I did my PhD in France at the Aix-Marseille Université.
Oh, right,
Yeah.
okay.
So
Good.
yeah, I can speak French too. So bonjour, je m'appelle Halikuddin Umasangaji, je fais ma thèse en France, mais c'était pas en paléoceanographie, mais c'est plutôt environmental chemistry.
Ok, très bien. Avec qui tu as fait ta thèse?
Je travaille avec professeur Pierre Doumenc à l'Université d'Aix-Marseille. Le labo, c'était à Aix-en-Provence.
D'accord, au CEREJ.
Yeah, c'est ça, au CEREJ.
Je travaille avec beaucoup de gens au CEREJ. Merci.
Yeah, au CEREJ, mon co-directeur, c'était Yann Cernoa. Peut-être que tu le connais.
Je
Mais il est
connais.
malade. Il est malade maintenant. Quand même.
Ya, terima kasih Pak Halikuddin, mungkin nanti bisa diskusi
terima
langsung
kasih banyak.
dengan Mary.
Merci.
Merci beaucoup.
Next question dari Pak Dimas, silahkan.
Yeah, greeting again. My name is Dimas, and I want to ask a question again.
No problem.
Okay, thank you. Some scientists say that the Earth's rotational velocity is getting slower. So does that phenomenon have any impact to the thermohaline circulation in the ocean? But then again, a slower rotation velocity may be leading to more oxygen in the atmosphere and ocean because the days will be increasing in the length and the phytoplankton called photosynthesis more. That's it.
Whoa. Okay. I'm not sure. I think if there are any changes in the Earth's rotation speed, it's happening so slowly that it's not going to have an effect on the next few decades. That's my first guess. After that, I'd have to think about it. So basically, if you slow the Earth's rotation, you're going to reduce the Coriolis force, and that will act upon perhaps the speed at which the gyres are turning. How that would affect global climate, I am not entirely sure, and I would have to do a bit of research into that. It's an interesting question from an oceanographic point of view. I don't think it's going to affect the predictions of climate change in the next few decades. Not significantly anyway, but yeah, a good question. I would have to inquire a little bit around me with my fellow oceanographers, like modern day oceanographers. They would be able to give me a more quantitative assessment of that impact. But interesting question. Thank you.
Yeah, you're welcome. It's no problem if you don't have any answer right now, and I will wait for the answer in the future. Thank you.
No problem. Definitely, I will be discussing that.
Yeah, thank you very much.
No worries.
Thank you. I think this will be the last question because time is up. It's almost. Maybe this last question from Madatila. Silakan, Mbak.
Terima kasih Bu atas kesempatannya. Okay, good morning, Prof. Thanks in advance for your nice presentation today. I have a question. When we check a data, for example, in checking sediment cores, there could be an error in the instrumentation. And my question is how to confirm the accuracy of the data we get. Thank you.
How do you, I'm sorry, I didn't hear the question, just.
How to confirm the accuracy of the data we get. Maybe in the taking in the data, there could be an error in instrumentation.
Okay, so you're talking about the potential error in the delta 018 measurement in the sediment cores. You're talking about uncertainties. Okay, there are uncertainties in our measurements, and these are basically translated into uncertainties in our estimates. And we work very hard to reduce these uncertainties, but they are inherent to our method. And for example, if I wanted to give you a quantitative estimate of our uncertainty, if you measure the delta O18 on a foraminifera, the average error is about 0.1. So if you translate that into temperature, that would be maybe a 0.5 degrees Celsius error. So that is something that we just have to work with. We are reducing the errors as much as we can. And another approach is to combine different proxies. So for example, myself and Sri Yudawati, Cahyarini, what we do is she measures corals and I measure bivalves within the same site, and we compare the two proxies. And if it is a robust feature, if they're telling us the same story. And by doing these kind of studies, we can come forward as a community and say with much more emphasis, this is the result of our study. And so this is definitely an important question. It's inherent to any scientific study that we have to deal with error bars. And there are different ways of tackling it. We are lucky in paleoclimate because we have different proxies, we can compare them. And that's an important process. I hope I answered your question.
Okay, thank you. Thank you, Prof.
No worries.
Okay, thank you. I think time is up now. And thank you very much, Professor Mary Elliot, for your time. And I think now I will give back to MC, Mbak Bila.
Okay. Thank you, Professor Dr. Mary Elliot, for the presentation. Merci beaucoup. It really gives a new insight for us. And also thank you to Bu Yuda, who led the discussion session very well. I hope all the participants get some new knowledge, especially about the Paleoceanography and Paleo-ENSO. And also thank you to the participants for joining our student course series 2. Just to remind you that we will have another series of student course in this semester with very interesting topics. For more information about the next student course, please stay tuned in our Instagram at oceanography.itb. So see you in the next student course. And once again, thank you for Professor Mari, Bu Yuda, and participants. Stay safe and healthy. Au revoir.
Thank you very much.
Bye-bye.
Terima kasih.
Terima kasih.
Thank you, Mary. Bye-bye. Bu Yuda, thank you.
Terima kasih.
Have a nice day.
Goodbye.
Bye.